Yes? Okay, that's something else. That is going into systems and linear equations. What we want to deal with today is just the inverse, right? So we're looking at this first of all. We want to get the inverse of this matrix. So there are a couple questions that I will definitely want you all to be able to answer before we actually jump into finding the inverse. So before we jump into finding the inverse, I have a question. How do we know whether or not a matrix will have an inverse? What are some of the things that we need to consider in order for a matrix to have an inverse? Ah, lovely, lovely. So there we go. Two things. One is that it must be a square matrix. And the second thing, as she said, also starts with an S. Whether or not the matrix is singular or non-singular. Alright, this is going to be important. So the first part of things, which is square matrix, is the matrix that we're looking at, the one that we want to find the inverse of. Is it square? Alright, so it is square. How can we tell that it is a square matrix? There we go. And this is a 2 by 2 matrix. So you see why it's important to be able to state the dimensions or the order of a matrix. Once you could do that, you could identify square, rectangular, column, row, whatever. You could tell the type of matrix you're looking at just by identifying the dimensions, the order of the matrix. So it's a square matrix. So we check off the first part. Now, singular versus non-singular. Anybody want to explain for me what we're talking about when we say singular matrix? Alright, so I heard two people overlap and say it, and I hear Mayasha very confidently come forward and she said, yes, that is when your determinant is 0. So lovely. When you have a singular matrix, the determinant is 0, right? And if it is non-singular, what do you think that means? So singular, it's a matrix with a determinant of 0. Non-singular, what do you think that means? There you go. Determinant is not 0. Simple as that. So it can be any numerical value as long as it is not 0. Now, this one, if we have to determine the determinant of the matrix. So I'm probably hearing Rex jumping around in the back there. Yeah. But if we have to determine the determinants of this matrix, earlier Renita told us that the determinant of a matrix, so I'm just using the notation I have on the board, right? So the determinant of a matrix M is AD minus BC. So can you all determine for me the value of the determinant for the matrix that we want to get the inverse of here? So I'll give you all a minute. See if you could work that out. Okay, so Carissa has an answer for us. Let's see what Carissa got. Carissa said she got, whoa, she got a big number. She said she got minus 22. Yeah, for the determinants. Alright, so I'm going to make note of the responses that we get. So Carissa said she got minus 22 for the determinants. Anybody else want to tell me what they got for the determinants? Alright, Nadiash. Ah, so Nadiash also got 2. Alright, so I had 2 persons for 2. Let's see what Sasha got. Sasha, Mayasha. Alright, so the 2. Look at that, even closer. Alright, so we have a lot of people saying 2. Alright, right now. There you go. Lovely. That's it. So I'm glad that you can correct your peers as well. You see, this is what I've always talked about. Within this classroom, this online space, I should say, I've always encouraged you all to identify your strengths and weaknesses, and when we work together, you all will realize that you can achieve much better things. So yes, Renita has corrected for us the little error here with this minus 22. Alright, so this is what I was saying. Direct numbers is going to be really, really, really important, and it's so interesting. We are in the year 2022. We have all these 2s here, and then there's this thing I saw the other day on Facebook. What was it? This year, February 2nd, so it will be the 2nd of the 2nd month, 2022, and that day will be a Tuesday, so you can literally say that that day will be a Tuesday, and I'm like, oh, okay. So yeah, lots of 2s this year. Anyway, determinant is what it is, positive 2, and like Renita was saying, 5 by minus 2 is going to give us a minus 10. And over here with this double negative, we have to pay attention to that, right? So this will give us minus 12. And this becomes a positive. And that's how we get minus 10 plus 12 is a positive 2. Alright? So, that's our determinant. So, if we have to classify singular or non-singular, what do we say about this matrix? Is it singular or is it non-singular? Non-singular, so the echoes of non-singular have it, and that's correct. It is a non-singular matrix. So now that I have identified that my matrix here is square, it is also non-singular, that tells me that this matrix can have an inverse. And earlier, I believe was Carissa had told us how we're going to get our inverse matrix. And she said, our inverse matrix, so let's just call this guy M because I want some notation, right? So if I want to get the inverse of this matrix, M inverse, so remember our notation as well. Notation is important. Notation, vocabulary, processes, everything. You see, maths is not just the numbers, alright? So M inverse is equal to 1, say that back? Yeah? Okay, like I was saying, whether you, okay, notation. Let me talk about notation quick. Notation is important. I named the matrix M. So I can't recall if I've ever said it before, but I just want to make sure I say it again, right? When it comes to notation and maths and problems where you want to work out something, you always make sure you put the notation in so you could quickly reference it. So like I just said, I'm going to call the matrix M, and that's why my notation will have M. If you had a matrix called A, this would be A inverse instead. If you had a matrix called D, you would have D inverse instead. Okay? So the notation doesn't mean that only if the matrix is called A means that you could get A inverse or find the determinant of matrix A or the adjoint of matrix A. The important thing to know is that if you have a matrix called M and you need to get the inverse of the matrix, this is the way that you get your inverse, but instead of writing, like you were saying, cursor A, you would write the name of your matrix. It kind of come like us in class. I mean, if I'm looking at the working that you might do versus somebody else, right? You might be using A because you're accustomed to A, but somebody else might want to use M, or somebody else might want to use some other letter. As long as you are specific about your notation, so you let me know that this is a matrix you're referring to when you do this, I have no problem then. Nobody will have a problem with it. We just need to see that, one, you know the process of obtaining your inverse matrix and you can properly execute it, which is what we're going to do now. Okay? So, across the board for everybody, notation, right? They didn't tell us the name of the matrix. They didn't tell us if it's A, if it's X, if it's P, if it's Q. If they don't, and you want to make your life easier with your notation, you give it a name and you use that name. Okay, just make sure you stay consistent. So, M inverse, this is the matrix M here. This is how I get my inverse matrix, and I want to get the inverse of matrix M. Alright, so from here, we do know how to get the determinant. We calculated the determinant earlier, as a matter of fact. We said the determinant is M, determinant of M is 2. Now, if I want to get the adjoint matrix, how do I get the adjoint matrix? Anybody? Oh. Beautiful. So our adjoint matrix will look like something like this, right? So we interchange the elements on the leading diagonal, and then we just change the signs of the other two elements, the ones on the non-leading diagonal. So if I want to get my adjoint matrix, so I'll write out the working part now. So M inverse is equal to 1 over my determinant being 2, and my adjoint matrix, I'm going to interchange those elements on my leading diagonal. So A is positive 5 and D is negative 2. So I'm going to switch the positions and put minus 2 where A is, and put 5, positive 5, where D used to be. And then B and C, all I'm going to do is change the sign. So over here, B is a positive 4. In my adjoint matrix, B is now going to be a negative 4. And then C, over here C is a negative 3. And in my adjoint matrix, it's going to be the negative of negative 3, which will give me a positive 3. Does everybody follow what happened with the adjoint matrix? Okay, so I heard a yes. Is there anybody who's confused? Raise your hand. If anybody is confused, raise your hand. Anybody needs anything cleared up? Okay, so Dominique is thumbs up. She said she's good to go. Everybody okay? Okay, day 3. Alright. So remember, in your adjoint matrix, to get your adjoint matrix, your original one, you're taking the elements on your leading diagonal. So when I say leading diagonal, I'm talking about these two guys here. They go interchanging. That's it. That's it. And then you're not needing, those stay where they are, but the signs have to change. So when your signs change, like we were saying, because B was a positive 4 initially, it becomes a negative 4 here. But then C was originally negative 3. So if I'm taking the negative of a negative number, that will give me a positive 3. Alright? So just in case some people were also not too clear on it, is that much clearer for you now? Where the positive 3 and stuff pop out from? Okay. No questions? Okay, alright, so Calissa gave a thumbs up, she's okay. Alright, let's progress. So like I usually would tell you all, because you want to calculate your inverse, you could stop at this point here, because this in itself says inverse. You can go further if you like and multiply each element in your adjoint matrix by the scalar here, and you will get a complete matrix as well. When you are working out products involving, like, say you have your inverse multiplied by something else, I would highly recommend you always multiply your scalar by your adjoint, so that way you just have matrices to multiply. Alright, no scalars outside, because sometimes people make mistakes when they leave the scalar outside and they try to do the matrix product and whatnot. So I would highly recommend always multiplying the elements inside your adjoint matrix by your scalar. So this would give me -1, -2, fractions that not many people are too fond of, but we get 3/2 and 5/2. Okay, also you could write it as a decimal. In the case where you might get things like recurrent decimals and stuff, I would prefer you leave it in the rational form like this. And I also personally find that sometimes you leaving it as a fraction makes it easier to do some of your multiplication if you have to do any further multiplication with your inverse matrix. Okay, so this is how we obtain the inverse matrix. Alright, so again, like I would always say, start off first of all by identifying whether or not the matrix that you're working with is a square matrix, and whether or not it is singular or non-singular. To assess whether or not it's singular or non-singular, remember your determinant. If your determinant is 0, then it is a singular matrix and you have no inverse. And if it is non-singular, then your determinant is going to be a non-zero value, and you can have the inverse of that matrix. To obtain your inverse matrix, like we said here, it's going to be 1 over the determinant of the matrix M by the adjoint of that matrix. Okay, and as I mentioned before, notation, I use M, you might use A, some people might use P, Q, R, S, T. As long as you know what matrix you're trying to find the inverse of, that is all that matters. Okay, once you're able to work out your determinant, you understand how to find your adjoint matrix, and you know how to do scalar multiplication, you will be able to obtain your inverse matrix. Alright, so that is that part of the question.